Welcome back. The objective of this video is to explore even and odd polynomial functions and their symmetry. So first let's look at even functions. An even function is a polynomial function in which every term will have only an even exponent. Now we can have a constant in an even function as well. So an even function will have all even exponents. Algebraically, we'll say that f of the opposite of x is equivalent to f of x, meaning whether we put -2 into a function or +2 into a function, we'll get the exact same output. And then finally, an even function is symmetrical across the y-axis, while an odd function is a function that has all odd exponents. And there can be no constant in an odd function. So we can only add 0. We can't add any other number, a 3, a 5, a 15, a 20. Can't happen. So all our terms are going to be have odd exponents or odd degree. Algebraically, we would say that f of -x equals the opposite of f of x, meaning like if we put 1 into a function and we get -2 out, well, if we put -1 into the function, the opposite of our original 1, now we're going to get the opposite answer out. So we'll get +2. And an odd function is symmetrical across the origin. So in example 8, we want to determine whether each graph is even, odd, or neither. Well, in A, we can look at this, and I would look at the symmetry, and I would say that this graph is symmetrical across the origin, and therefore it is an odd function. But we can also look at this numerically. We can see that f of 1 equals -2. So then, using the odd function, if we put -x in, so now we do f of -1, well, we put -1 in and we get +2. So we see here f of the opposite of x equals the opposite of f of x, right? F of x was -2, so we put -1 in, f of -x, and then we got +2 out. In problem B, what kind of symmetry does this have? Well, this is symmetrical across the y-axis. So this is going to be an even function, and it's symmetrical across the y-axis. Algebraically, we would say that f of the opposite of x equals f of x. So if I put something like, well, let's use, boy, I don't have really many good points here. But if we used, we'll just say f of 3/2 appears to be about -2. So that would mean that f of -3/2 better also equal about -2, and it certainly does. So we would say f of the opposite of x is still equal to what we get when we put x in, equals f of x. And problem C, this guy is neither. We don't have symmetrical across the y-axis, and we're not symmetrical across the origin. Example 9 asks us to algebraically determine whether each of the following functions is even, odd, or neither. We're going to cheat here a little bit. We'll do this algebraically in just a minute. But we can see here we have a second degree and a first degree. 2 is even, 1 is odd. So we've mixed our evens and odds. We already know this guy is going to be neither even or odd. But let's go ahead and do our algebraic check. So our function f of x equals x² plus x minus 12. So let's see what happens when we put -x in. So f of -x equals -x² plus a -x minus 12. We simplify the right-hand side. We get positive x squared minus x minus 12. So f of negative x doesn't equal our original function. It doesn't equal f of x, but it also doesn't equal the opposite of x. So f, because we don't, all of these aren't opposite signs. So f of negative x doesn't equal f of x, and f of negative x doesn't equal the opposite of f of x. So this is neither. Problem B, x to the fifth minus 4x cubed. Each of these exponents are odd. We only have odd exponents. There's no constant. So this is going to be odd. We'll prove that algebraically by putting in negative x into our function. So the opposite of x to the fifth minus 4 times the opposite of x cubed. We still get negative x to the fifth, or we get negative x to the fifth there, times negative 4 times negative x cubed. Multiplying this, we get negative x to the fifth. A negative times a negative is a positive, plus 4x cubed. So each one of these is an opposite sign. So in our case here, f of negative x equals the opposite of f of x. That is an odd function, and it'll be symmetrical across the origin. And in problem C, y equals 2x to the fourth minus 6x squared. I have only even exponents, so we already know the answer. This is going to be an even function. Even if I added a number here like 3 or 15, that is still going to be an even function. That's going to shift that up or down on the y-axis, and it's going to maintain its symmetry. So let's check this out algebraically. We'll put negative x in to our function and see what happens. So negative x to the fourth, I have an even number of negatives, so that's going to be positive, so I end up with 2x to the fourth. Negative x squared is going to become positive again, and I get negative 6x squared. And that is the exact same thing that I started with, so f of negative x does indeed equal the same output as f of x, and that is an even function, and it'll be symmetrical across the y-axis. Example 10 says determine the symmetry that the graph of this equation will exhibit. We have 9x minus x cubed. Well, each of these are degree 1 and degree 3. Those are odd numbers. This is going to be an odd function, which means it's going to be symmetrical across the origin. We'll justify that by checking what happens and do this algebraically. F of negative x equals 9 times negative x minus negative x to the third. So we get negative 9x plus x to the third. These are both opposites, so now we see f of negative x does indeed equal the opposite of our original function, f of x. So that is an odd function, and it'll be symmetrical across the origin. And we'll get some more practice with this when I see you in class.